The last sections we covered identified the differences between first and second order reactions and how the rates adjust as you change the concentration of these reactants. In, again, the first order reaction, as you double the concentration of reactant, in this case reactant A, you're also going to double the rate at which the products are formed. Again, these can only be determined experimentally, in which you'd have to compare one trial versus another trial. Again, in the rate reaction, you have the rate constant times the concentration of said reactant raised to the first power. Now, we're not going to deal with calculus, but the non-derived version of this formula can be used to determine the concentration or the pressure of A at any time throughout a first order reaction. What we have is the natural log of the concentration of A at a particular time divided by the concentration of A initially, or A naught, is equal to the negative rate constant times the time that we're looking at. When we manipulate this equation, it results in a formula that resembles y is equal to mx plus b, which is the formula of a straight line. Now notice again, natural log of the concentration of A at a particular time is equal to the negative rate constant times the time plus the natural log of the concentration of A initially. Henceforth, when we plot the natural log of A versus time, we should get a straight line with a slope of negative k. This negative k is the same k used in rate constant. Using this logic, let's consider the process in which methyl isonitrile is converted to acetonitrile. What we have is a graph of pressure of the reactant versus time at a particular temperature. In this case, it is 198.9 degrees Celsius. Now, the first thing to note is the pressure drops over time. That simply means that the reactant is being used up as the reaction progresses. Now, what we did with this last time is we were able to determine the instantaneous rates of any point within the reaction. If you recall, we did the tangent line for the particular time we're looking for. We did rise over run, and we were able to graphically determine the rate at that specific time. Now, what is unique to first order processes is that if you were to take the natural log of the concentration or the pressure of this particular reactant and plot it versus time, you do get a slope that equals negative k, which is the negative rate constant. This again only occurs in first order processes and identifies it as a first order process. Question number 1. The decomposition of a certain insecticide in water follows first order kinetics with a rate constant of 1.45 per year at 12 degrees Celsius. A quantity of this insecticide is washed into a lake on June 1st, leading to a concentration of 5.0 times 10 to the negative 7th gram per cubic centimeter. We're going to assume that the average temperature of the lake is 12 degrees Celsius. A. What is the concentration of the insecticide on June 1st of the following year? So we're allowing the reaction to go for a full year. And B. How long will it take for the concentration of the insecticide to drop to 3.0 times 10 to the negative 7th gram per cubic centimeter? Again, the question identifies this as a first order process. Since this problem is asking us to solve for first order kinetics, we have to go ahead and write down the formula. The insecticide is the concentration that we're concerned about, so we're going to substitute A with insecticide. And since we're looking for the concentration after 1 year, we're also going to substitute 1 year with time. Also note that to get the natural log of A by itself, we had to add the natural log of A at time 0 to both sides. When you solve this out, the most important thing to understand is that we have this negative 16, but that's equal to the natural log of the insecticide. That's not the concentration. So in order to find the concentration, we will need to E both sides. That takes care of the natural log on the left-hand side, and it gives us our true concentration on the right-hand side. Question B is looking for a particular time. So we're going to plug the numbers in and try to rearrange for time. In order to do that, to get time by itself, we're going to have to subtract the natural log from both sides. Oh, sorry, we're going to have to subtract the natural log of time 0 from both sides. And then we're going to have to divide both sides by the rate constant, which is negative 1.45 per year. This way we do have t by itself. Keeping track of units, the rate constant is a per year, which means that when we solve for time, that will be year also. Question 2. The decomposition of dimethyl ether at 510 degrees Celsius is a first order process with a rate constant of 6.8 times 10 to the negative fourth per second. If the initial pressure is 135 torr, what is the partial pressure after 1,420 seconds? Again, the question tells you it's a first order process, but even if the question did not tell you, you could probably gather that from the rate constant unit. Per second is quite obviously a unit associated with first order kinetics. If it was per molar per second, then you would identify it as a second order kinetic unit. Again, this question clearly states that it's a first order process. Your best bet is to simply write down the formula and try to figure out what to do with it. The major difference between this question and the previous question is that it wants the answer in terms of pressure instead of concentration. That's fine. These types of problems generally do substitute pressure for concentration and vice versa. Once you rearrange the formula, you'll notice you're solving for the natural log of the pressure at 1,420 seconds. Don't forget, you cannot stop once you do all the math, because once the math is done, it's actually for the natural log, not for the pressure. So to get rid of that natural log, you're going to have to E both sides, and don't forget to include the unit that you need. Similarly, the integrated rate law for second order reactions also results in an equation that mimics y is equal to mx plus b. But this time it's a relationship between 1 over the concentration of A versus time. When we look at this graphically, a plot of 1 over the concentration of A versus time will yield a straight line with a slope of positive k, again the k being the rate constant. When we look at practice problem number 1, the following data is given to us for the gas phase decomposition of nitrogen dioxide at 300 degrees Celsius. As time increases, the concentration of the reactant decreases as expected. But the question ultimately is going to be, is this a first order or second order reactant? To do that, we're going to have to take the natural log of the concentration first. If we plot the natural log of the concentration versus time, we are looking for a straight line. In this case, we do not get one. That simply means this is not a first order process. We have nothing left to do except to graph 1 over the concentration versus time. And what we have is a positive slope which identifies this as a second-order kinetic reaction. If for some chance this did not come out to a straight line, the best thing that we could say about the reaction is we don't know what order it is. It's definitely not first. It's definitely not second. Who knows if it's third order, fourth order, whatever. Consider again the decomposition of nitrogen dioxide discussed in the previous question. The reaction is second order with K is equal to 0.543 per molar per second. Again, you'll notice that the rate constant is indicative, the unit at least is indicative of a second order process. If the initial concentration of NO2 in a closed vessel is 0.05 molar, what is the remaining concentration after 1/2 hour? This question clearly states that we're using second order kinetics. So again, we start with our formula. And since we're looking for the concentration of NO2, we substitute A with NO2. The time that we're given is 0.5 hours. The problem with this is that our rate constant unit and our time unit are not the same. Our rate constant is in per seconds. So we're going to have to take our half hour and we're going to have to convert that into what it would be for seconds. This way you have the units canceling each other out. After you do the math, you have a simple ratio of 1 over the concentration is equal to a particular number. Then you basically just cross multiply and solve for x. Half-life is determined through the study of kinetics. It's defined as the time it takes until the concentration drops in half. Now what we could do is we could determine half-life graphically, or we could determine it mathematically. If you take a look at the graph, what you would do is you would look at two instances in the graph, one denoting half of the original sample, so 75 versus 150, and simply how long it takes to go from 150 down to 75. In this particular case, we're looking at roughly 13,000 seconds. If we were to take a look at 75 versus 37.5, we would start at roughly 13,000 right here, and we would end at roughly 27,000. So the time is about 13,000, 14,000 seconds. Graphically, it might be difficult to identify, but the half-life of a reaction should never change over time. So any 2 points that you pick should be fair enough. For first-order reactions, the half-life is a function of the rate constant only. The initial concentration has no influence on the half-life. It's worthy to note that radioactive decay is a first-order process, and we will be talking about that during the nuclear chemistry unit. Now, technically, the half-life of a first-order reaction is the negative natural log of 1/2 over K, but if you take the negative natural log of 1/2, you'll always get the same number, which is 0.693. So you can simply figure out the half-life by 0.693 over the rate constant. Again, be on the lookout for your units. The second-order reaction shows a significant difference when calculating the half-life. The half-life is a function of the initial concentration of the reactants, not only just the rate constant. The reaction of chlorobutane with water is a first-order reaction. This figure shows the concentration of the chlorobutane changing with a particular time at a particular temperature. A. From the graph, we're going to estimate the half-life of this reaction. B. Use the half-life from A to calculate the rate constant. Again, to graphically determine the half-life of a first-order process, you need to select two concentrations, one in which is half of the original. Then you're going to have to find the time that each of these concentrations are present and simply subtract. So in this case, the half-life should be 350 seconds, and that will be a constant regardless of which concentrations you select. To determine the rate constant of this particular reaction, since it is first order, it would have to be the half-life is equal to 0.693 over the rate constant. So you simply solve it, cross multiply, and you get your rate constant. Question 2. Using the equation, calculate the half-life for the decomposition of the insecticide described in the previous section's question. How long does it take for the concentration of the insecticide to reach 1/4 of its initial value? So this question is in reference to the insecticide question that we did previously. In that question, we were told that the rate constant is 1.45 per year. Now, since that was a first order process, we can determine the half-life by taking 0.693 and dividing it by the rate constant to get the half-life. Next, the question asks, how long does it take for the sample to decay into 1/4 of its initial state? Well, we're starting with one full sample. After one decay, we'll have half the sample. After two decays, we have 1/4 of the sample. So, 2 decays, each decay takes 0.478 years. Multiply that by each decay, and we have 0.956 years. Temperature has a significant influence on the rate of reaction. Generally speaking, as you increase the temperature, the rate of the reaction also increases. The only thing that can influence the rate constant is the temperature. What this means is a particular reaction will have different rate constants at different temperatures. When studying reactions, the most important thing to think about is the particles colliding. In a chemical reaction, bonds are broken and new bonds are formed. Molecules can only react if they collide with each other. On top of that, they must collide with sufficient orientation and enough kinetic energy to cause the bond to break and reform. You have to know that the molecules are constantly in contact with each other and are constantly colliding. But unless they collide at the proper angle with the proper speed, a reaction is not going to take place. In other words, there's a minimum amount of energy required for the reaction to take place. This is known as the activation energy. Just as a ball cannot get over a hill if it does not roll up the hill with enough energy, a reaction cannot occur unless the molecules possess sufficient energy to get over the activation energy barrier. What we have here is known as a potential energy diagram. A identifies the reactants or the energy of the reactants. B identifies the energy of the products. The difference in B from A is the enthalpy of the reaction. So remember, changes are always final minus initial. Since B has lower energy than A, this reaction is exothermic or loses energy. The energy required to get up to the top of the hill so that the reaction can proceed is known as the activation energy. The top of the hill is known as the activated complex. It is the point in which the molecules have rearranged themselves with enough kinetic energy and orientation so that the reaction may proceed to the product side. If the reaction is reversible, the activation energy for the reversible reaction is from right to left instead of left to right. In this particular case, it is more difficult to go backwards than it is forwards. Consider a series of reactions having the following energy profiles. Assuming that all three reactions have nearly the same frequency factors, rank the reactions from slowest to fastest. Simply put, the faster reaction should have the lowest activation energy. Reaction number 1 has an activation energy of 15 kilojoules per mole. Reaction 2 has an activation energy of 25 kilojoules per mole. The forward reaction for reaction 3 has an activation energy of 20 plus 5 kilojoules per mole. That means reaction 2 and 3 both have the same activation energy and should be equal in terms of rate. Number 1, which has lower activation energy, should be the fastest. In the Arrhenius equation, activation energy may be calculated if you know the temperature, the gas law constant, and capital A, which is the frequency factor. The frequency factor is a number that represents the likelihood that collisions would occur with proper orientation for the reaction. Knowing that the value of the rate constant changes with changing temperature, the Arrhenius equation can be used to experimentally determine the new K at a new temperature based on the fact that you know a baseline K at a baseline temperature. Again, this reaction identifies a y is equal to mx plus b relationship, which means that the slope of the line will help to determine the activation energy. The following table shows the rate constants for the rearrangement of methyl isonitrile at various temperatures. From these data, calculate the activation energy for the reaction. What is the value of the rate constant at 430 Kelvin? Use the data from the above question. Calculate the rate constant for the rearrangement of methyl isonitrile at 280 degrees Celsius. So what we have here is a fairly lengthy question in which all of the answers pretty much are going to be transferred to the next question. So biggest problem is to figure out where to begin. Question A asks for the activation energy. Now, technically the activation energy can be solved using the following equation, but the problem is A is the frequency factor, and we don't know it, nor do we really care about it. So in order to solve for the activation energy, we're going to rely simply on the slope of the data. Now, the slope is equal to the negative activation energy over R, which is a gas law constant. Now, we need to figure out the slope by taking the change in the natural log of the rate constant, which is data given to us, divided by the change of 1 over temperature, which is also data given to us. So we're going to determine the slope for the second part right here, and then we're going to transfer the slope into the formula of equals negative activation energy over gas law constant. So we're going to take the data and we're going to write it down. And we only need 2 points. Okay, the 2 points here is going to be enough to give us our slope. So since we need the natural log of K, I'm going to make another column and calculate the natural log of K. And since we need 1 over temperature, I'm going to make another column and determine that value also. But also it's worth noting, and this is important, the temperature must be in Kelvin. So before you could do the 1 over temperature, you have to convert your temperature from Celsius into Kelvin, and then you have to divide your Kelvin by, or divide 1 by your Kelvin temperature. Now changes are always final values minus initial values. So in this case, I would take the lower of the 2 values on the data table that I gave to you and treat it as the final. So for change in the natural log of K, what I would do is negative 9.85 minus a negative 10.6, and then I would divide it by 0.002119, because that 2119 goes with the negative 9.85, minus 0.002161. So when you solve that out, that is going to give you the value for your slope. Okay, so your slope is negative 1.79 times 10 to the fourth per Kelvin. Now what we do is we take slope is equal to the negative activation energy over the gas law constant. The R value, remember there are a couple different R values, but since we're dealing with activation energy, we need to deal with it in terms of joules. Now this value of R should be 8.31 joules per mole Kelvin. So negative activation energy is going to be equal to negative 1.79 times 10 to the fourth times 8.31. So our negative activation energy is minus 149,000 joules per mole, or our activation energy is 149,000 joules per mole. Now activation energy always needs to be a positive value. This question is all about changing rate constants with changing temperatures. Question B is asking about the value of the rate constant at 430 Kelvin. Now, activation energy is specific to a particular reaction, so it should be constant for the reaction regardless of the temperature. So what we do is we're going to set up a relationship between a known rate constant value at a known temperature, and we're going to compare it to a new rate constant at a given temperature. In this particular case, the lower of the two temperatures must be T1, which means that the rate that goes along with it is going to be K1. What I selected as the baseline is the very first data on the table, a temperature of 189.7 degrees Celsius, which is equivalent to 462.7 Kelvin. What we're basically doing here is we're plugging in the known activation energy, the gas law constant, and then 1 over temperature 2, which is the higher temperature, minus 1 over temperature 1, which is the lower temperature, both in Kelvin, and we're setting it equal to the natural log of K1 over K2, which is the K associated with the higher of the two temperatures. Once you do the math, notice it is equal to the natural log, so we have to get rid of that natural log by e'ing both sides of the equation. This way, we have K1 over 2.52 times 10 to the negative fifth is equal to 0.0573. Solving for K1 is equal to 1.44 times 10 to the negative sixth.